Hello again. In this short lecture, we'll talk about thermal expansion. We know that most materials expand as temperature increase. So let's take an example. Let's say I have a rod of length L naught at temperature T naught, right? So you can think of this knot as your original. So original temperature, original length. Now, if you change the temperature of the rod from T naught to T naught plus delta T, then its length will increase. And let's say that change in length is delta L. So now the new length is L naught plus that delta L. If you increase further by another delta T temperature, then new temperature T naught plus 2 delta T, and the length of the rod is L naught plus delta L plus delta L. So that means 2 delta L increase. And if you keep going on 3 delta T or 4 delta T, we see that this is also changing 3 delta L, 4 delta L, all those things. So we can summarize this result that change in length is proportional to change in temperature, right? So that's one relation we can see. Then also we see that delta L also directly proportional to L naught. Here it is. Let's say again same thing. Initial temperature T naught, original length L naught. When you change the temperature by delta T, so T naught plus delta T, it became L naught plus delta L. How about this? If I have the original temperature T naught, but length now being 2 delta L, 2 L naught. So now the original length is twice that what we have here. And if you change by the same temperature delta T, what will happen now? You will see that if your original length is twice that the previous one, and for the same change in delta T, it happens that your change in length is also twice, although the temperature increase was same as their L naught. So from here we can conclude that change in length is also proportional to your original length, what length you started with. So if I combine these two observations, and then we can say the delta L is proportional to L naught, the original length, and the change in temperature. Then we can write the delta L is equal to some constant of proportionality, let's call it alpha, and then we say L naught and then delta T. This alpha is called coefficient of linear expansion. So this one we can say this is the relationship, mathematical relationship, and alpha is called coefficient of linear, because we are talking about linear length, linear expansion, right? Coefficient of linear expansion. And of course the unit is SI unit of this is per Kelvin, or also you can use per degree Celsius. Okay. All right. Okay. So that's for linear expansion. Similarly, we can say that, let's say, so that was linear expansion, right? We can talk here also about this volume expansion. So let's say talk volume expansion. Right? And volume expansion. So let's say the V naught, and object was V naught is my original volume at temperature T, at initial temperature, at original temperature or initial temperature T naught, right? And as you change the temperature T naught to T naught plus delta T, the volume changes. And let's say, so then I say dV is change in volume due to the increase in temperature delta T. So let's write due to increase in temperature delta T, or delta dt, or this is just symbol thing is all delta T. Okay, so I can say the change in volume dV is equal to, I can write it dV derivative of volume with length times del L, or we can write it, let's say d over dl and L cube, this is dl. So if I do this math here, this becomes 3L squared dl, right? And remember, what is L? L is the new length. So here, if I look at this, what is L here? So from here, I can write, from here, I can write delta L, L minus L naught is equal to alpha L naught delta T, because that's changed. So L is your new length, right? Or increased length, or L is equal to L naught plus alpha L naught delta T, right? So remember this. So same is that L I'm putting there. So if I take the square, both sides, L is square and then whole term is square, we see the alpha is not typically very small. Alpha is 10 to the power minus 6, right, of that order, 1/1,000,000th order. So this term is very, very small compared to L naught. So when we square it, it becomes further smaller. So L is square is same as L naught is square. So I can write it here that 3 L naught squared. This is kind of approximation, but it works. And then dl, if I take the derivative dl, then or take the difference, dl is alpha L naught delta T. So that's changed. So I can write it alpha L naught delta T, right? And if you do this math here, let me jump from here to, I'm running out of space, maybe let's write it down here, and then I can write it dV is equal to this L naught square, and L naught becomes L naught cube. So I will write it here. So 3 alpha, L naught cube is my original side, so I can say this is my original volume V naught, right? And then I write delta T. So, or I can say dV is equal to beta V naught delta T, which is similar, or I can write it delta V. This is just a symbol, which symbol we use. So we can say change in volume is equal to beta V naught delta T. What is beta? We just saw we replaced beta for 3 alpha, right? And alpha was my linear coefficient, a linear expansion coefficient. So beta is 3 times the coefficient of linear expansion, and this one has a name. You can think that the coefficient of volume expansion, coefficient of volume expansion, right? Okay, so this is a formula we got for volume. Great. So as we know that most of the material will increase in length or volume as the temperature increases. So if I look at water and the temperature is increasing, the volume of the water increases. So no problem there, right? However, if you look at closely at very small temperature between 0 and 10 degrees Celsius, something anomalous, something abnormal we see. And what do we see? That as we are lowering the temperature, the volume is decreasing. So that's fine till a point is reached till 4 degrees Celsius, and then from 4 degrees Celsius to 0 degrees Celsius, the volume starts increasing again. So this is This kind of behavior by water is called anomalous behavior of water right at this. So from 4 degree Celsius to 0 degrees Celsius, instead of although temperatures going down, so instead of decrease in length or volume, the volume increases, and this behavior is very important for marine life during winter time. As the temperature is going down, when temperature is going down, let's say from 10 degrees Celsius towards the 4 degrees Celsius, the density increases because volume is decreasing, density decreases. So the volume, the water at the top of the lake, let's say, goes down. But once this reaches at 4 degrees Celsius, and as the temperature is going further down, then this temperature, this volume start increasing, then it becomes lighter, and then it starts coming up. So that way lake freezes from the top. So on the top, when the temperature is, let's say, below 4 degree, it still is lighter, so it stays up, whereas leaving the water underneath at 4 degrees Celsius. So water freezes from the top up, keeping the marine life alive. So very important feature for this, or important feature for this water behavior to keep the marine life alive.